Welcome back. So hopefully you've had a look at those other videos on 3 Blue, 1 Brown and Brett Finney's channel and figured out a bit more about how the data work on a mass spec. So what we get out of this is a mass spectrum, and I hope that now you appreciate where that comes from. So we have some kind of a frequency that we've now measured, and the step I haven't really talked about yet is calibration, and that's essentially a way of getting from the frequency to the correct mass to charge ratio, and that's something that we do weekly, I suppose, on the mass specs, sometimes more frequently, sometimes less, it depends. But we have a mix of specific molecules that we know all the masses of, and we spray that into the mass spec, and we update our mapping between frequencies and mass to charge ratios based on the mass to charge ratios that we see when we spray that solution. And that means that then we can go on and measure a whole bunch of different samples and be really confident about what the mass to charge ratios are that the instrument is reporting to us. And you can see here that, I hope you can see that on the spectrum in the background, these labels are the mass to charge ratios of these peaks, and they have 4 decimal places, and that's about 300. So it depends on what resolution we're running the instrument at as to how long it collects the data for, and then how accurate it can be. But at this kind of a mass, we would expect that 4th decimal place to move around a little bit. And so there's always some tolerance that we have to work with. But at least the 3 decimal places before that, we expect to be pretty sound. And on this instrument, we work in ppm tolerances, parts per million. And we do expect to see, on a wild sample, less than 5 ppm. Less than 5 ppm error, which means then if we're going to go and look at, figure out what these molecules are, we don't have to use a tolerance any bigger than 5 ppm, which is nice and narrow, and it helps us a lot. If we zoom into one of these peaks, there's actually more information that we can get out of this. On this type of instrument and many others, we can discriminate isotopes. So if you imagine, let's say we've got a molecule with N carbons in it, and it has some other stuff too. Then in the wild, there'll be 1% carbon 13. Most of the carbon is 12. So actually what we'll see is some of that molecule where all the carbons are carbon 12, but we'll also see some of that molecule where one of the carbons is carbon 13, and then the rest of the carbons are carbon 12, and then whatever else is in there. And there'll also be some where 2 of the carbons are carbon 13, and the rest are carbon 12, and so on. And so we get these discrete peaks corresponding to the different isotopes. Right, get rid of that out of the way. Okay, so so this guy here, 404, they are presumably this all carbon 12 copy of this molecule. But then 405, this one has a single carbon 13. And I'm just going to remove this actually and say that this one has 0 carbon 13s. This one has 1 carbon 13. And this one has 2 carbon 13s. And actually, there's stable nitrogen isotopes and others as well. And these all contribute, but carbon is the most abundant at about 1% in the wild. So this is the one that we see the most of. And the important piece of information we can get from this, well, there are kind of two, but the main one, in an instrument, in any instrument that can do this, you know that what you're measuring is mass over charge. And you know that the difference between these isotopes is approximately 1 mass unit. And so, let me tidy up a little bit there. Right, so you've got mass over charge, but then this one is going to be mass plus 1 over charge, and this one is going to be mass plus 2 over charge. And so if your charge state is 1, then that plus 1 will be plus 1. But if your charge state is 2, then that plus 1 will be divided by 2 overall, and so the actual gap between your isotopes will be a half. So in this case, we can guess that the charge state is 1, and so the mass is actually whatever the mass to charge ratio is, and then corrected for a proton or something like that. But if the gap between these peaks was a half a mass unit, or half a mass to charge unit, so that would be here somewhere, then we would know from that that the charge state has to be 2 in order to explain that being there. And then we know the charge state. The thing is, if we know the charge state, then we can multiply everything by the charge state and we get the mass out. So when we talk about mass spectrometry, in this case, we are actually talking about mass because we can figure out what the mass is, even though what we're measuring is acceleration in the first instance. And then we're mapping that onto mass to charge ratio. Because we have these isotopes, we can figure out what the mass actually is. And one other thing I wanted to point out, if you did watch the 3 blue 1 brown video, when you zoom right into these peaks, so when you're zoomed out, they look like sticks because they're so narrow. But when you zoom right into them, they do have this kind of bell shape, just like the peaks in the Fourier transform video. Okay, so now we know what the 3 dimensions of our data are. And in a room of people, I would stop and ask the question, what are the 3 dimensions of the data? And then I would pause, and maybe someone would come up with 1 or 2, and hopefully people will come up with all 3. And they're on the slide, so I'm sure you get it by now. We have, first of all, that this is LC-MS data, and the LC part of this gives us a retention time or an elution time, the time that a particular molecule came off the column. We then have mass to charge ratio, which we can interpret as being mass, but we only ever plot mass to charge ratio on these things. And that's our second dimension. And then in our third dimension, we have this kind of signal intensity, which gives us an idea of how much of that ion was present, and at least enables us to compare between different samples whether anything has changed. What are the dimensions? Oh yeah, there are lots of peaks in a typical experiment that we do. So if you cast your mind back to the UV trace that I showed, there were very few peaks there. But when you have these 2 dimensions of retention time and mass to charge ratio and a complex biological sample, there can be tens of thousands or hundreds of thousands of peaks. And we like to group them together based on their isotopes. So you might think that this one and this one belong to each other because they're different isotopes of the same ion. And in that case, you would group these together and you would call that a feature. But even still, there can be tens of thousands or hundreds of thousands of features in one of these ion maps. And it's quite a challenge to figure out what they all are. So figuring out what they are is called identification, and it varies depending on what kind of thing you're trying to identify. And there are some quite critical problems, actually. So for example, these 2 molecules, adenosine and deoxyguanosine, they both have the same molecular formula, C10H13N5O4. and so their masses are the same, 267.0968. So how do we tell the difference on the mass spec? And this is another point where in a room of people, I would stop and pause and wait for someone to answer this. So maybe you want to, as 3 blue, 1 brown says, pause and ponder and think about what might be the answer to this question. So there are 3 potential ways that these things could differ. One of them we can't really use as a tool because we can't rely on it. But I'll say that one first, and that is that different molecules of the same mass may ionize differently and end up in different charge states. So they could have a different mass to charge ratio. But again, we can't really rely on that. The second thing is we're using LC-MS, and so we're trying to separate the different molecules in time. So hopefully these 2 molecules would come off the column at different times. And we could use standards. We can buy stuff from, I was going to say the name of a company that we buy chemicals from, but I'm not gonna. But you know, we could buy stuff from a famous chemicals company and inject it on the LC-MS system and see exactly where the peaks come off in time. And then we know if we see a peak there, that's probably the thing that we're after. So that would be a nice way to discriminate these 2 things. And the final thing is we can use fragmentation, which I talked about previously, but we didn't go into detail, so let's do that a bit now. So for fragmentation, let's recap, right? We have ions coming off the HPLC here, they get ionized here, they come through the instrument, and for fragmentation, we're interested in the fragments of a particular ion. And so we isolate that particular ion using our mass filter, the quadrupole. So I'm going to take a slight tangent and talk about how that works. The quad is quite a complicated thing to think about, really. It's called a quadrupole because it has 4 poles. They have a specific shape that's optimal for controlling the ions in them, and they are electrically connected in opposite pairs. The ions come in at one end like this, and they come out the other end, or they don't come out the other end because they've been filtered. And the way that they're filtered is by the superposition of 2 voltages. One of these voltages is a DC voltage. That is a fixed voltage between the 2 plates. It's a voltage offset of a particular number of volts, and it doesn't change. For a particular isolation, it doesn't change. And the other is an alternating voltage, and this is fluctuating backwards and forwards between the 2 pairs of poles. The purpose of the voltage offset is to cause ions to drift towards one set of poles, like this picture in the middle. And larger ions, that's not right. Ions with a larger mass to charge ratio will do this. They will drift off towards one of the poles. And in order to stop them doing that, you have this alternating voltage, and it kind of pulls the ions back into the center, like what we see in the bottom. And this is kind of the Goldilocks situation where everything's just right and the ions can come out the other end. If they're too big, then they're not affected enough by this alternating voltage, and this drift happens. If they're just right, then they are corrected, and they manage to spiral through the quadrupole and come out the other side. And if the mass to charge ratio is too small, then they accelerate way too quickly and they spiral out of control, like in the picture in the top there. So essentially, you have a range of mass to charge ratios that will pass through the quadrupole, and everything else kind of drifts out of control or spirals out of control and ends up hitting one of the poles and gets stuck there. And for that reason, if we're using the quad a lot, we do need to take it out and have it cleaned every few months. there is a coarse filter on the front of the QE Plus, Q Exactive Plus, and on the Fusion Lumos. That means a lot of the stuff that we want to throw away gets thrown away a lot earlier in the instrument in a component that's easier to clean, but it's not a very good component in terms of the isolation that it does, but it keeps the quadrupole cleaner anyway. But the quadrupole itself, if you could do with some space here, if you were to draw a mass spectrum, the isolation shape might be something like this in the ideal scenario. It doesn't really look like that, but basically you're getting rid of everything that has these ranges of mass charge ratio and accepting everything that has this. And you can make that nice and narrow, so you can select a specific ion of interest. And back to the point of why we're talking about this, the reason you want to select a specific ion of interest is because you want to fragment it. This is a simulation I did of how the quad really works. So these previous pictures in the middle here come from this web page, which actually doesn't exist anymore, which is a bit of a shame, I think. But they show a kind of a two-dimensional view. So this shows a three-dimensional view. You're looking down the end of the quad, and the ions are starting somewhere in the middle. And then I've just gone step by step in time and figured out where they're going to go next based on what the field strength is within this space inside the quad. And so on the left, there's one that's spiraling out of control really quickly. That's one with a mass to charge ratio that's too low. On the right, there's one that kind of drifts out of control very slowly. And this is one whose mass to charge ratio is too large. And in the middle is one that made it all the way through the quadrupole because it was just right. So it comes out the other end of the quadrupole. We're selecting mass or mass to charge ratio 267 and maybe plus or minus 1 or something like that. And that ends up in the fragmentation cell. And in this type of fragmentation, you're just bumping it into some gas. So I said previously, the whole of the mass spec is a vacuum inside. And that's not quite true. There's gas in some places to help slow ions down, like in the C-trap. Things arrive in the C-trap, and there's a little bit of gas in there to help the ions slow down. And you may have noticed that slowing down on the thermo video of the Q Exactive. And in the HDD cell, there's gas in there. And it's the same with ion trap fragmentation as well. There's gas in there, and you bump the ions into the gas and they fall apart into characteristic fragments, and then you can measure them. And this is what they look like for these particular two molecules. We have a peak at 150 and a peak at 134. And those are characteristic fragments of these two molecules. This is the fragment for deoxyguanosine. This is the fragment for adenosine. And so that's the third way that you can tell these things apart. And quite a reliable way in many cases. We can also fragment peptides. And this is the basis of bottom-up proteomics, where we take a sample, digest all the proteins, and fling them on the LC-MS and see what we get. And the data that comes out of that is based on this fragmentation. What you get from that for HCD and CID is fragmentation on the peptide bond, which gives you a spectrum that might look a bit like this. So from the right, fragments are called Y ions, and the number is the length of it. So this Y7 ion here corresponds to this sequence here, ELLLNVK. And the next one is Y6, and that corresponds to all of that sequence minus the E. So you know that this gap here must be the residue E. And what you can do, if you're really keen, is look at a spectrum like this and figure out what the different amino acids are in the sequence based on the gaps between the peaks. And it's not something that's done very often, to be fair, because it's quite difficult. The software, there is software that can do this to some extent, but it's not as powerful as what we normally do. And what we normally do is run the whole experiment inside a computer and compare the results. So we take a sample in real life and we take a sequence database representing our sample. We digest the thing in real life and we digest the thing in the computer. We run it on the mass-spec and get the fragmentation spectra. We generate fragmentation spectra in the computer. And then we compare all the fragmentation spectra together and figure out which ones look the most similar and are most likely to describe the data properly that we've acquired. That's a whole other video, by the way. So we'll leave it for there, and I will see you in the next video.